Hello and welcome back to the Advanced Malware Analysis course by myself and Vitaly Gromez. So in this first part we're going to be focusing on injection techniques, and we're going to cover a lot, so it's quite a long one, so let's just jump straight into it. So to start off with, let's have a look at the different methods of injection. So first we've got self-injection. So this is used commonly in malware unpackers, although sometimes it's found in malware trying to keep everything inside of one process. So an example of that is Gootkit. And the second method of injection is remote process injection. So this is very common in malware from script kiddie level to APT level. There are multiple different techniques to use with different levels of sophistication. So let's have a look at the different techniques we're going to be covering. So to start off with, we've got DLL injection. This executes a malicious DLL inside of a remote process. Then we've got PE injection. This executes a binary or shellcode inside of a remote process. Then we've got process hollowing. This will execute a process and suspend it, overwrite the original process in memory with malicious code, and then resume the process. Next up, we're going to be looking at process doppelganging. This will overwrite an executable content with malicious code, load that executable into memory, roll back the overwritten executable, and then finally execute the executable from memory. If this is quite confusing, don't worry, we're going to be looking at all of these in depth, as well as reverse engineering malware that uses each of them, so don't worry, we'll get to it. Next up, we're going to be looking at Earlybird and APC injection. So these both use asynchronous procedure calls to execute malicious code in another thread. We're going to be looking at the differences between the two. Next up, we have API hooking. So this is BockBot, or IcedID, as it's also known as specific. So this hooks API inside of a remote process in order to execute malicious code when the API is called. So this may be found in other samples, but we're going to be focusing on the most common one, which is BockBot. And finally, we've got the propagate injection method. So this injects code into processes by taking advantage of the way Windows subclasses its window events. So now we've covered the different methods of remote process injection we're going to be covering. Let's have a look at DLL injection. So how does it work? So to start off with, we have a malicious executable and a path to a malicious DLL. The executable will allocate memory with the size of the path to the DLL. It will then write the path of the DLL to the recently allocated memory, and then it will call load library in the legitimate process through a call to create remote thread. Now the argument passed into load library will be the path to the malicious DLL. So this is essentially forcing the remote process to load the malicious library. So this is just an overview of how it works, a basic summary of it. So we're going to be doing this for each injection method. Then we're going to look at the pseudocode used in each injection method, and then finally we're going to actually reverse engineer these techniques. So now we're going to look at recognizing the API. So the common API used is open process, virtual allocate X, write process memory, get process address, create remote thread, and then wait for single object. It could also use some file commands like get temp path or something if it stores the malicious DLL in the temporary directory, or it might have a hard-coded path. It all depends on the malware. So now we know some API to look out for, as well as the functionality of DLL injection. Let's have a look at DLL injection in malware. Okay, so we're going to take a look at DLL injection to begin with. Though as DLL injection isn't as common as it used to be extremely popular among a lot of different malware families. However, that's since changed now that attackers and basically everyone has realized that you can inject an executable or shellcode into process memory, or use a different, more stealthier technique, as this method has been done millions of times and antivirus has basically perfected the art of detecting it. So this is actually a sample I have developed. It's another one I'm working on, and this uses some basic DLL injection. So as we scroll down, we can see it's loading a resource. It's doing all the resource stuff here, and this is just loading the DLL into memory. So we have a call to create toolhelp32 snapshot. As we scroll down, we can see it's calling process 32 first, and this is where it's going to loop around the different processes, and it's going to compare the name to a specific value somewhere. Let's see if we can find this. Okay, so here we call open process. It will push ESI. ESI is the process ID. So somewhere here ESI is set, and here we can see that ESP plus 428 plus PE.th32 process ID. So before this, the comparison is done. So this is where it will basically jump to open process, or it will call sleep and loop back around. So this XOR here is triggered in a few different places, specifically when it fails to get the next process from the looks of it. If we jump back to the top here, it seems that it will be triggered when the program fails to get the next process. So if all the processes have been checked, then it will call this XOR. And so let's take the path back to where the comparison is most likely done. So here we move an unknown value into EAX, and we compare this value in EAX to DL, which contains a value in ECX, which is the name of the process executable file. So this would be explorer.exe, iexplore.exe, notepad, chrome.exe, whatever. So this value here is encrypted. We don't know what it's comparing it to, though the process it's looking for is stored in there. You can basically follow this back, find cross-references to find where it's being decrypted. So we know that it's going to be opening a specific process, and then it will allocate a region of memory inside of that process, with the size being 0x104, which if we convert to a decimal is 260. And the value 260 is actually the max path variable in Windows. So the max path that a file can have is 260 bytes or 260 characters. So if we go ahead and press M, it will allow us to search for a standard enumeration. Click yes. Now if we type in max underscore path, we can see that the value is here. So it's going to be allocating a region of memory with the size max path. I believe this differs on different machines. So Windows XP has a smaller max path. I'm not too sure about that. But anyway, we know that it's allocating a size that is the max path size. So it's a good hint that potentially DLL injection is occurring here. Although in some cases, they might just simply use the size of the string they're writing into memory. In this sample, that's not the case. So once it has called virtual alloc, it will move buffer into ECX and move ECX plus 1 into EDX. It will then move ECX into AL, increment ECX, test AL, and then loop back around. So I'm not sure what's going on here exactly. From a quick look, it seems to be incrementing ECX, possibly a size. I think it might be trying to get the size of the string by incrementing it each time, and as it's pointing to a memory address, we then subtract ECX from EDX, which is a pointer to ECX plus 1. So I'd assume that this is getting the size of the string to write to process memory, which would make sense. So it will then push all of this data plus the buffer. Obviously that's encrypted as well. And it will push that to a call to write process memory. So here we're writing a string into the open process. And immediately after that, we push EDI, which is the address of the allocated region of memory, so the return value from the virtual alloc. So we're pushing EDI, and then we push load library A, which is the start address, and then it pushes ESI, which is the process handle, and then calls create remote thread. So what this is going to do is it's going to call load library and then pass in the address of the allocated region of memory as the argument. So from a quick look, this looks like it's trying to load in a region of memory, but because we have written some data to that allocated region, it's going to be trying to load whatever has been written to that region. So if this is a file path, it will try and load the file from that file path. So this is extremely easy to notice. If you see something being called with create remote thread and having load library A being passed to it, you know it's trying to load an additional DLL. So this is from a graph perspective, so the basic disassembler view. But if we go ahead and view the pseudocode, click OK, it will become a lot more clear what's going on. So v14 in this case is the return value from virtual alloc x, which is the allocated memory. And Then we have v13, which is the process handle, and it will write in buffer, and buffer is equal to, let's say, a file path. It is. I'm not going to tell you exactly what it is. I need to do a few more changes to this, so it's not going to be exact if I do use it as a capture the flag thingy like another sample we're going to be looking at, but I don't want to give too much away. So it'll write a path to a DLL into the allocated region of memory. Then it will create a remote thread passing in load library. So this will essentially call load library in the remote process, passing in the allocated memory as the DLL to load. So that pretty much wraps up the very basic DLL injection. Now, I didn't want to, cover this and then just leave it and move on to the next one, because there is another method of DLL injection that is a lot more commonly used, although I still think it's quite rare, and that is reflective DLL injection, which is actually, now I think about it, one of the main injection methods used by Metasploit, and because it's been covered by so many people, most likely for a lot of malware like ScriptKiddie malware or basic malware as a service. And so as a result, I decided to throw that one in as well, and we're going to go ahead and jump onto looking at a sample that uses reflective DLL injection. So let's go ahead and jump into that now. So DLL injection isn't as common anymore in its original form, and that's mainly due to the fact that it requires dropping the DLL to the disk. And so a lot of malware authors tend to use something that is more fileless, which allows for a more stealthier approach, such as PE injection or APC injection or something like that. And to be honest, who needs to write a DLL when you can simply just compile your code into an executable? However, a couple of years ago, I can't remember exactly when it was released, a new method of DLL injection was developed by Stephen Fewer, and this basically involved injecting a DLL into a process without it ever touching the disk, and this injection was actually named reflective DLL injection. So it works similar to regular PE injection, where you'll have the DLL in a resource or something, you'll read that into memory, and then you'll essentially map the DLL into an allocated region of memory, and then write that into the remote process. So I have here a basic explanation of reflective DLL injection from Stephen Fewer's GitHub repository. So first, execution is passed either via create remote thread or a tiny bootstrap shellcode to the library's reflective loader function, which is an exported function found in the library's export table. So the sample we're dealing with today in this part is actually ransomware, and luckily for us, they've decided to rip out all his code and pretty much use it for themselves. So we have a reflective loader function here. This may not be the case all the time, although the method of execution will be the same. So as the library's image will currently exist in an arbitrary location in memory, the reflective loader will first calculate its own image's current location in memory so as to be able to pass its own headers for use later on. This reflective loader will then pass the host process's kernel32 export table in order to calculate the addresses of three functions required by the loader, namely load library A, get procedure address, and virtual alloc. The reflective loader will now allocate a continuous region of memory into which it will proceed to load its own image. The location is not important, as the loader will correctly relocate the image later on. This is where the similarities between PE injection and DLL injection come into play. So the library's headers and sections are then loaded into the new locations in memory. The reflective loader will then process the newly loaded copy of its image import table, loading any additional libraries and resolving their respective imported function addresses. So this is basically loading in the import address table and loading in the required DLLs. So if it's trying to communicate out, this is where it will load in WinINet and write it into the import table. The reflective loader will then process the newly copied of its image relocation table, and it will then call its newly loaded image entry point function, which is DLL main with the DLL process attach flag. Now the library has been successfully loaded into memory from memory itself, and the reflective loader will then return execution to whatever called it, whether that's shellcode or create remote thread. At this point, the DLL would be loaded into a remote process, and the reflective loader would then go ahead and call something like create remote thread, pointing to the DLL main inside of the remote process. So it's essentially PE injection, although using DLLs. So let's go ahead and jump straight into it. So here we've got the reflective loader, and this isn't actually called anywhere inside of this process. I believe there's a stage before this that will end up calling reflective loader and injecting it into a remote process, but there aren't any cross references inside of this binary. If we go check the offset, it doesn't have anything really useful here. So let's jump to the reflective loader and start scrolling down. So we can see there's a lot of instructions going on here. There's not many API calls, and that's because this is essentially shellcode running that doesn't have access to API. So it doesn't have any addresses of get procedure address, load library or anything. And so it's got to manually resolve all the addresses for everything, similar to how shellcode does that. And so if we start from the top, we can start to see some values that make sense. So here we see this value, which is the 5A4D, so the MZ header. So here it's basically checking to make sure that, okay, there's definitely a header here. And here is the PE header. So it's passing the PE header of the DLL here. It will then query the process environment block and search for loader and then in-memory order list .flink. So this is a lot of theory stuff to delve into, and so I will cover that a lot more in depth when it comes to the PDF alongside this. However, to sum it up, it's basically a list of the DLLs that have been loaded into memory in order. So I believe NTDLL is the first thing to have loaded in. So the first value here will be NTDLL, second one will be kernel 32, and so on. So this is essentially just looping through the different modules that have been loaded into memory. So as we go down, we can see it enters this while loop here, and 46 seems to be the size of the loaded module. So it will loop around, subtracting 1 from 46 on each loop. And what it's doing here is it will pass v31, which is equal to 0, into this subroutine here. It will then rotate it right by 13, return that into v32. It will then check to see if the character in v24.flink is less than 97, which is A. And if it is, it will then add the value to v32. Otherwise, it will subtract 32 from the v24.flink byte and add that to v32. So what's going on here basically is they are hashing the different loaded modules and they're converting it to uppercase before hashing it. So they'll hash kernel32.dll, and then once it has hashed the string, it will compare v31, which is our hash at this point. They'll compare it to 06A4ABC5B. So when looking at API hashing, it's important to look for comparators. So for example, if you see a function being called with the first argument being a strange hash, then what you want to look for is anything that compares the first argument to anything inside of the function. So like here we see v31 being compared to this hex value. This is an immediate sort of hint that there's probably API hashing going on here, especially when you're looking at shellcode, or maybe just looking at malware that uses custom API hashing like Zloader or Dridex. So luckily for us, this is a very common hashing algorithm, and obviously we could approach this by replicating the hashing algorithm, although because it's been used so often and it's very common, what we can go ahead and do is we can sort of treat it like how we approach encryption algorithms by using it as a constant. So we can go ahead and literally just paste the hash into Google and you'll come up with loads of different responses. This was the first web page I could actually access using Internet Explorer. I should probably go ahead and install Chrome on my static machine. But anyway, we can see here that it will compare EDI to 06A4ABC5B, which is equal to kernel32.dll. Now we know that it's checking for kernel32.dll. We can sort of guess what's going on here. It's then going to go ahead and get the address of kernel32. So here it seems to be getting the address by using v43, which is equal to j and then 2 and then flink. It will then call this function here, which is another API hashing function. And this time it will do v43, which at this point I'm guessing is the base address of kernel 32, plus v15, where v15 is a pointer to the export table. So we can see v15 is incremented on each loop. And what it's doing is there's a export table which has a list of functions and a list of addresses to those functions. So incrementing v15 will get the next function. So v43, I'm guessing, is probably a pointer to the export table or a pointer to the export name. And v15 seems to be a counter. So we can see v15 is incremented on each loop. Although if we jump into this function, we can see that it will loop around and increment a1 on each loop. So I don't think this is a counter. I think this might be the offset of each API name. So this is incremented if it cannot find any of the targeted libraries. So the return value is the hash of the API, and it will then check to see if it's equal to any of these three values here. And these three values are actually load library, get procedure address, and virtual allocate. So it will check to see if any of these are equal to those three API. And if they are, then it will go ahead and locate the address of the API specifically. So v43 is going to be a pointer to the export table. And from there, it will use this information that it's gathered to locate the exact offset of the API call. Then it will check again to see if it's equal to these functions. So it can individually store it in functions. So rather than going, yes, v8 will contain this, it has no idea what API it's passing off to the variable, but in this case, it will check again. So I believe this is load library, and if v13 is equal to the hash of load library, it will move it into v8. If v13 is equal to get proc address, it will move it into v13. If v13 is equal to the hash of get proc address, it will move it into v7. And then finally, if it's equal to virtual alloc, it will move it into v10. So this is just going to loop through all of the exports of kernel 32 until it finds the correct values. And this will continue looping until it's found all three API addresses. And we can see that v47 here is decremented on each successful loop. So it's set to 3 by default, and once it's found all three API addresses, it will be equal to 0, and this while loop will exit. That's for loading in the functions from kernel 32. Now, there's also another section here that will load in different API from another DLL from the looks of it, and in this case it's 3CFA685D. So let's copy that out, head over to the fastest browser in the world and hit enter, and we have a few different GitHub repositories here. Annoyingly, Internet Explorer won't load it, although we can see in the description the NTDLL hash is equal to that. So we know now it's going to be looping through the exports of NTDLL and seemingly trying to load this function here. This could be a NT-resume thread or something. Let's go ahead and do the same thing we did before. And it's actually a hash of NT-flush instruction cache. So it'll try and load that. This is the same hashing routine again, the rotate right by 13, and it will loop around that until it locates it. So this time v48 is equal to 1, so it will loop around until one API has been discovered. And from there, what it will do is, now it's loaded in all the necessary functions. Let's go ahead and quickly name these. Now we know which one's which. This is load library, I believe. Load library. This is get proc address, and this is virtual alloc. And then we have the flush instruction cache here. So now we have all four functions that it loads. We can see it calls virtual allocate. So this is where it will allocate a region of memory to map the DLL into. Then this is basically the whole relocation step. So it will pass the relocation table and basically see where each section should be mapped into memory. So the .text section will be at offset 0x400 normally to begin with, and when it's mapped into memory, it's at offset 0x1000. So once it has mapped it all into memory, and basically copied everything to the allocated region. It will then go ahead and build the import address table. So here we can see it calling load library. So it will pass the DLL again, checking for the different imports it requires. It will load that library in, store that in v22, and then seemingly pass it by hand or simply call get proc address. So that will store it in M, which will store it in the newly allocated region of memory. And once the IAT has all been constructed, we'll then move on to locating the export to call. So here we can see v42 is equal to v18 plus 40 plus v45. So this will essentially look for the DLL main export to call, which I'm not sure if there's one in here. Doesn't look like it, so I assume this could be used for an external process and loading it into memory. Obviously not too sure about that as I haven't looked into it too much, but we can see it calling v42, which is equal to v18 plus 40 plus v45. So v18, if we scroll up, we can see is equal to I, and I is equal to the base address of the DLL, because here we can see that the value in I, the first 2 bytes, is being compared to the MZ header. So we can assume that I is equal to the original base address of our DLL, so before it's been mapped into memory, and v45 at this point is most likely to do with the allocated region of memory. And as we scroll up, we can see that v45 is equal to the return address of virtual alloc. So v45 is linked directly to the DLL that's been mapped into memory, and v18 is equal to the DLL that isn't mapped into memory. So once it's got the correct address to execute, so the DLL main or a start function, it will then call it, passing v45, the value 1, and the argument passed to this function here. So reflective loader, it takes 1 argument. So that pretty much sums up the reflective loader stuff here. It's almost identical to PE injection, as I mentioned before. There's a few more things to it, like fixing the import address table and all that stuff, as well as calling the export of the DLL as opposed to calling the entry point. I will have a PDF to go alongside this, as this is quite a complex thing, especially with all the process environment block passing. It's useful to know, the different things, like we've got in-memory order module list, but there's a few different other module list orders. So I believe there's an in-load order module list, which has NTDLL first rather than kernel 32, which in this case, I believe in-memory order module list is kernel 32 at the top, but in load order list, I believe it's NTDLL. So we'll go into depth on that in the PDF. And yeah, so that pretty much wraps up the stuff on DLL injection. We've had a look at both reflective and regular DLL injection. And so I believe in the next part, we're going to be looking at APC injection. So let's go ahead and jump onto that now. So with DLL injection covered, let's have a look at PE injection. So it's very similar to DLL injection, except in this case, we're actually going to be writing the executable into memory directly rather than loading it or anything. So to start off with, we will allocate memory with the size of the malicious code, whether it's shellcode or an executable. Then we will write the code to allocated memory. If the code's an executable, it must be loaded into memory, so it's got to be mapped correctly, otherwise it won't run. And then finally, the malicious executable will execute the code inside of the legitimate process using a call to create remote thread. So when you go ahead and run an executable, Windows will go ahead and load it into memory. It'll automatically map the sections of the executable into memory. However, in this case, we're actually loading the executable ourselves, so we have to do everything manually, so emulating the Windows loader. It's actually quite easy to recognize inside of malware when it does this. Let's go ahead and look at the API used when it comes to PE injection. So we've got open process, virtual allocate X again, write process memory, virtual protect X, create remote thread, and then wait for single object. So again, very similar calls. However, in this case, we are not writing the path to the executable, we're writing the entire executable into memory. So let's go ahead and reverse engineer a malware sample using PE injection. Okay, so I have a sample of Parallax Rat here. Now, it's a highly obfuscated piece of malware, and So performing static analysis would take a real long time. We'd basically need to map out the API hashing routines and all those sorts of things that will allow us to figure out what API is being called. So what we're going to go ahead and do is firstly perform some behavioral analysis and then create a few assumptions based on what we see from that, and then go ahead and jump into a debugger and perform some dynamic analysis, putting breakpoints on different API calls that may be involved in the injection process. So this methodology is mainly used when you have a sample that will unpack itself into another process, and rather than analyze the unpacking routine, you just want to get the unpacked payload as soon as possible. So let's go ahead and open up Process Hacker, let that open. So with Process Hacker open, let's go ahead and run the piece of malware. Obviously we're inside of a VM, so let's run that. So we see it spawns and it seems to be doing something, and then it will execute this MSTSC process, which is going to possibly contain the malicious payload. Let's see if it does anything else. It seems pretty dormant, although now it's starting to unpack something. Okay, now we see it's created cmd.exe in a suspended state and resumed it. Now the first two exit and we're left with cmd.exe. So at this point you'd suspend that, you'd go into the memory regions and you'd search for read write execute, and you could say that this is possibly shellcode. Could be shellcode, not too sure, but you'd basically look for an executable inside of memory. So here we've got 172 kilobyte region. We'd click that, and this is possibly the malicious executable that was injected into Explorer. We can see that we can see a path to the run once string, so looks like persistence is being established somehow. Scrolling down briefly, let's see if we can find these strings. It doesn't look like it. So if you're going to basically go for speed and unpacking, you'd go ahead and dump that out right now and then go through it and look at it. But in our case, we're interested in how it will actually inject into a process, how it will actually inject into the first process, and then you can go ahead and do the same steps to figure out how it injects into CMD. So let's leave that suspended just in case they have a persistence mechanism set up that if it doesn't detect cmd.exe, it will go ahead and spawn another process. So let's open up this para-rat inside of X32 debug, and we're going to want to put a breakpoint on a few different things. So to begin with, obviously we need a breakpoint on create process internal W, and we're going to want to put a breakpoint on NT write virtual memory, and I think that's most of the ones we want for now. Like there's only two main ones. If we see it calling create process internal, we can make our decision on what to put breakpoints on then. So let's go ahead and run the debugger, run it again. Hopefully it should hit the breakpoint soon. Okay, so we've hit NT write virtual memory. This seems to be writing memory inside of its own process, so nothing really helpful here. Okay, calls it again. Seems to be calling it several times, but here we go. We finally hit the call to create the MSTSC process. So let's hit the return on this. It will create it as suspended. So now it will call write virtual memory, and basically the first few calls to NT write virtual memory aren't exactly to do with writing the malicious code into it. So this is mainly done as part of the process initialization, and normally you can tell which ones to avoid because of the size. So here we've got the size 0x20 being passed in, so 32 is writing 32 bytes, and obviously that's not going to contain an executable. So let's keep running. Okay, now it writes 0x34, now it writes 4 bytes, and we hit a breakpoint. So remember how we hit the return? It finally hit the return. So if we take the return again, so now we end up in the parallax rat payload. So let's go ahead and resume execution. So now we hit another breakpoint on NT write virtual memory, and this time it's writing quite a lot of data, so 0x7924 bytes, and it's writing it to the address 8006C. So what we should have done is probably put a breakpoint on NT allocate virtual memory to see it actually allocating virtual memory. But in this case, we now know it's performing some write operation with a lot of data, possibly an executable. Let's right click, follow dword in dump. and it doesn't seem to be an executable, although I'm guessing it's probably shellcode of some form, as there's no reason it would write this large amount of data to a process without it being anything, unless it's an encrypted executable that is decrypted in memory. So let's right click, follow on disassembler, and obviously it's definitely shellcode. It's pretty clear that if it wasn't shellcode, this function here wouldn't exist. It would be a load of random data like we see here. So rather than writing an executable into memory, it's going to go ahead and write shellcode. So now we know that. Let's go back to where we're executing from. We want to write the process memory. So now we're back in the Parallax RAT memory space. And we're going to want to put a breakpoint on ZW resume thread. And the reason for this is it will allow us to stop execution of anything until we have a debugger attached to MSTSC. So now if we run the debugger again, we hit another call to NT write virtual memory. Now this is writing a URL to the binary, it seems, possibly filling in the shellcode. So if you went ahead and dumped the shellcode before it wrote this URL, you wouldn't be able to find the C2. Not entirely sure why they do this, but obviously they are doing it. So let's continue, run again, and we hit a breakpoint again on NT write virtual memory. This time we're writing 0x4c bytes, and we're writing this data here. So this is, it doesn't seem to be code, possibly just a structure of some sorts. Following disassembler, yeah, it doesn't look like anything really. If we scroll up a bit, is there anything there? Nope. Okay, so possibly something just used by the process itself. Let's see, how long is 4c bytes? So I'll write all of this data to it. This looks like offsets inside of the NTDLL library, and if we actually follow D1 disassembler, it does appear here, although I think that might be a coincidence. I'm not too sure. Follow D1 disassembler. Okay, so it is actually calls inside of NTDLL. So this is ZW delay execution. If we follow D1 disassembler, this one just seems quite strange. I think that might be a different value or used for something else. We then have this here, follow D1 disassembler. Okay, that's a return. So it looks like what it's doing is it's writing some basic API that's been loaded in to the process. So let's go ahead and jump back to the instruction pointer. So we're writing that data. Let's run the debugger again. Now we're writing some more data, this time to the 9940 base address. And we're writing quite a lot more data actually. Let's follow this D1 dump. So this seems to be some more shellcode. But as we scroll up, we can actually see the .text section and the .rdata section, as well as the MZ header. So Parallax RAT will inject both an executable and shellcode into the remote process. If we scroll down a bit, we might be able to find some strings. It doesn't look like it, but if we go ahead and right click this, follow on disassembler, view strings, it will give us all the strings for the section. Obviously, there's nothing really there, mainly because it's a highly obfuscated sample. So it will write that executable to MSTSC. So let's run once more. It calls NT write virtual memory again. This time it's now writing 5 bytes to the offset 4F5D2E, which is quite interesting because it looks like it's writing to its own process, as this is a valid memory address inside of the Parallax RAT process. So if we follow D1 disassembler, obviously you can see that there's no useful data here, but it could be writing something. However, the important thing to take note of here is the first argument passed, which is actually the handle to the process it's writing the data to. And just a quick tip, if you have Process Hacker open, you can click the process, go to handles, click this button which will sort it all from lowest to highest, and you can see that 0x128 is a handle to the MSTSC process. So now you know it's writing the virtual memory inside of this process. So now we know it's definitely writing to this address inside of the MSTSC binary. Let's go ahead and view that. Let's go to memory. So the base address of this would be 4 followed by 5 zeros. So if we check this region of memory, we can see that there's a 4B followed by 4 zeros. So if we now click this, look down a bit further, we can start to see some more addresses, specifically a 4F5 followed by 3 zeros, which is basically this address. So this 4FD2E is inside of this region. So what it's doing is it will actually overwrite data inside of the MSTSC binary, and the data that it's going to be overwritten with is this data here. So let's follow dword and dump. So immediately I've noticed an E9, so it seems to be overwriting a value inside of MSTSC with a jump to something. So if we follow in disassembler, you can see it's a jump to an offset. If we actually follow that, it won't work inside of our own process. But what we can go ahead and do is take note of this address here. Let's open up something like Notepad really quickly and just take note of it. So it is 4F5D2E. And now we know that, we can go ahead and allow the write function to exit. So let's execute to return. Now let's open up another debugger, and we're going to attach to the MSTSC process. Now we go to memory map, scroll down, let's right click this, follow in disassembler, and now if we do Control G, it will allow us to jump to an address. So the address we're jumping to is this. So let's select that, copy and paste, and click OK. So now we can see that there's a jump to this 9 followed by 40 address, which if you remember, that's where the parallax rat ended up writing data to. And interestingly, X32debug provides us some symbols of this function, and the symbol for this address is the entry point. So what it's essentially doing is performing some basic API hooking on the entry point in order to divert the program to execute its own function. So similar to how IcedID does it. However, in this case, it is overwriting the entry point rather than any API calls. So once this program is executed, the entry point will obviously be called, and that will end up diverting it to this shellcode here, which has the URL. So this is probably going to be responsible for downloading the payload. So the reason it's done this is because when it comes to executing code inside of a remote process, you end up needing to either change the address of the entry point inside of the function. So when it comes to executing your own code inside of a remote process, you either need to select your malicious code as the main thread and execute that, or execute it as a separate thread alongside the main binary execution. And to do that, you would need to use something like create remote thread, potentially QUser-APC, which are all detectable by antivirus. But in this case, all it's doing is overwriting the entry point to end up calling its shellcode, so it avoids any of those thread execution instructions. And the only things antivirus can catch it with is the NT-write virtual memory, which is quite low level, and a lot of the time they have valid uses. So let's put a breakpoint on the entry point, and let's continue looking at our debugger. So now if we run it again, we hit another NT-write virtual memory, and this time it seems to be overwriting code inside of NTDLL, and it will write 5 bytes inside of NTDLL. It doesn't seem to be writing anything useful though, which is quite strange. It's literally writing the same data to it. Run again. Okay, it does the same thing. So let's search for NTDLL. So here we have NTDLL. Follow in disassembler, and it's writing it to this address here. We want to right click, binary, edit, copy this address here, jump back, Control G, paste that in. So it's going to be trying to overwrite the data for CSR identify alertable thread. Not entirely sure why it's doing that, possibly to avoid any antivirus hooks. So what antivirus will do is it will hook certain API calls like NT-write virtual memory, and this will actually end up being a jump to its own antivirus code. So what Parallax might be doing is overwriting that hook that the antivirus has placed on the API call, so it will call the actual function as opposed to the antivirus function, though not too sure about that, just a guess at this point. So let's go ahead, run it again. So it'll do the same write virtual memory for NTDLL. Let's keep running until we see something else happen. Still doing the same. Not entirely sure what these functions have. They all seem to have a jump though, so I'm guessing that's probably why. I think it will search initially for antivirus hooks, and if it finds like an E9 opcode, it will try and change it to its own E9 opcode. So let's keep running. At some point I might go ahead and disable the NT-Write virtual memory, just because at this point I'm pretty certain they've written everything they need to. So it is running constantly. Okay, and it looks like it may have resumed our process. It didn't end up hitting the breakpoint on ZW resume thread, which is quite interesting. So that could be another method of anti-analysis they use. One way to find that out is simply run this mstsc process and see what happens, and immediately it'll hit our entry point. So if we follow the entry point, we can see now that it has all the code here, the malicious shell code that was written, and it will go ahead and do its nefarious tasks. So that pretty much wraps up the process or PE injection that we're covering for this chapter. This is pretty much the process injection. It will inject shellcode and an executable, which is interesting to see. And yeah, so I think in the next video we're going to be looking at APC injection and the early bird process injection, which also involve process injection just with more stealthier techniques. So yeah, let's go ahead and jump on to looking at that now. So now we've looked at DLL injection and PE injection, let's move on to process hollowing. So now we've got two executables. It may just be one, it might write its own self into memory, but let's just assume we've got two executables here. So the first executable will go ahead and execute and suspend a target process. So this could be SVC host, this could be Explorer.exe, Chrome.exe, something like that. So the malicious executable will then go ahead and wipe the original executable from the process memory. So you'll have svchost.exe running, but the svchost binary won't be present inside of the legitimate process memory, if that makes any sense. Next, the malicious executable will go ahead and allocate memory in place of the wiped executable, and then it will write the malicious executable into that region of memory, and the process is resumed. So this is quite common in less sophisticated malware. It's very noisy, and so a lot of antivirus will detect it, but it's quite common when you're looking at stuff like Remcos or Agent Tesla. So it's always good to know. So let's have a look at some API used in process hollowing. So you got create process A, NT unmap view of section, virtual allocate X, read process memory, write process memory, virtual protect, get thread context, set thread context, and resume thread. So these are ones to look out for. Normally it's difficult to differentiate between this one and some other injection methods, although the main thing to look out for is the create process A call. If it passes the create suspended flag, then you know it's probably going to be using some form of process hollowing. And a lot of times you'll notice that process hollowing is being linked with other injection methods, and that's also quite common. I believe it's potentially process doppelganging that process hollowing is being used alongside. So those are some injection methods to look out for as well. So now we have an overview of how process hollowing works, as well as the API to look out for. Let's actually go ahead and reverse engineer a sample that uses process hollowing. Okay, so now we're going to go ahead and have a look at some process hollowing, and in this case I am using an example from my own sample I've been working on. I don't want to give too much away about it, so we're just going to be looking at the process hollowing routine, and I'm not sure whether I'm going to provide this as a sample for the advanced course or for the beginner course, but I'll see when I've got around to completing it. So it uses some basic process hollowing. Obviously the function will change before I release it as a CTF or a challenge for the course. So what you learn here isn't going to be exactly what's inside the sample, so it shouldn't ruin it too much. So it uses some basic API hashing, and I've just gone ahead and named this create process A. It will start off by creating a SVC host process, and it will create it in a suspended state. We can see the for flag passed here. It'll then pass v13 into this subroutine here, and v13 is the process information. So let's step into this function here, and immediately we've got NT unmap view of section. So the way IDA has passed this information is quite strange. There's some weird instructions here that I'm not too sure about. I think this is just overcomplicating what it actually does. So this is essentially a process information structure, and all it does is moves the process information.hthread into hthread. So let's rename arg0 to process info. Refresh everything. Okay, so I've just realized I'm not using dark mode. I'm not sure which is better. I personally prefer using dark mode, although some people might prefer the light mode. So I'm just going to go ahead and swap it over to dark. So obviously it calls get thread context, and it's getting the thread context of the H thread from the process we created. Obviously there's a lot of error handling in here. You sometimes see this in malware. Often, they'll implement some error handling. A lot of the time it won't be there, and it will just assume that you've managed to get the thread context. So once it's got the thread context, it will then read the process memory and store that in buffer. So it will read 4 bytes. So seemingly the MZ header or something, and it will store that in buffer. Then we move that into V8 and LP address into V9. LP address is equal to what seems to be the base address. I'm not too sure. So it will go ahead and read process memory. Then it will check to see if buffer is equal to LP address. And then it will call get module handle and then get procedure address and pass in the NT unmap view of section. This will then call NT unmap view of section, passing in the process info.m128i_i32. So what I think has gone wrong here is IDA has incorrectly analyzed this structure, and so instead of calling it a process info structure or a process information structure, it is deciding to assign it to a different one. So if we go ahead and right click this and jump to structure definition, we can see that this isn't the process information structure, and I actually have no idea why this has been created. So let's go ahead now and insert a struct type, add standard structure, sort by type name. There's a lot of stuff here. Okay, and we want process information, which we can find here. So now we have a process information structure. Jump back to the function and right click process info. Now we want to set IVAR type and change this to process information. Click OK. And now it has sort of neatened up the code a bit. We can see that it's now got H process, and hopefully we've also got H thread somewhere. So this just makes it a bit easier to read what's going on. So here we can see it is reading from the created process, reading it and storing that in the buffer, and it's actually reading data from the thread context. So as we go down, it will then call NT unmap view of section and pass in a handle to the SVC host process as well as V7, which is a pointer to buffer, which in this case is the read process memory. So this is basically going to clear out and memset the SVC host process, so there will be no SVC host binary inside of its process. So once we have called NT unmap view of section, it will then go ahead and call virtual alloc x, which will allocate a region of memory inside of the process with the size of the current executable. So v12 is equal to the allocated memory. This is then stored in LP base address, and if it failed to allocate memory, then it will check the last error and then attempt to allocate some more memory. And if that fails, then it will just print a debug message saying error at virtual alloc x. So it will then call the write process memory and write the base address to v5, and v5 in this case is equal to the thread context. So it is writing content EBX plus 8 to the remote process at the allocated region of memory, and it writes 4 bytes. And what it will do then is it will go about checking the relocations of the executable. So it will pass the executable, so the current one, to locate the .reloc section. And what it will do then is it will loop through, basically checking to see which section needs to be put where. So for example, the .text section, when it's unmapped, is at 0x400, and when it is mapped, it's at 0x1000. So this is basically what it's checking to see, and it will loop through the reloc table and basically check this for all the sections. Once it has done all this parsing here, it will then call set thread context, set the context of the thread, obviously. So to start off with, it will call write process memory, which involves writing the value in v25 to LP base address, and v25 is equal to LP buffer, which in this case I believe is the file we are writing into process memory. Now, it doesn't write the whole file instantaneously, it will actually write the headers first, and as you can see, it will enter a while loop here, which will call write process memory. So it will first write the headers into the process memory, and then it will change the protection of those headers to this value here, which I believe is read write. So once it's changed the protection, we will call write process memory on it in a while loop and constantly be writing the sections to the region of memory. So v45 is incremented here. It's incremented by 10 each loop, it seems. And once it's written the process memory, it will seemingly check for the protection of the sections. It will then set v50 to the protection it's supposed to be, and v50 is then passed into a call of virtual protect x. So this is essentially a method of checking to see, for example, does the .text section need to be read write execute, does it need to be read, and then it will basically loop around .text, .data, .rdata and check to see the protection of each. And this basically emulates the Windows loader. So once we have written everything to the process memory, changed all the protection rights, it will then go ahead and simply call resume thread, and we set the thread context earlier. So here we have context, and it basically is set to v16, which is equal to the allocated region of memory. So what this does is it will change the main thread to point to the entry point of our written executable. So now SVC host no longer exists. We need to redirect the thread to point at our own malicious executable, and therefore resuming thread will end up resuming the main thread in the binary, which points to our process. And at that point, it will be running under the name SVC host from the system32 directory. It's not really a good privilege escalation method, as I believe they patched that from happening a while ago. And so, yeah, that pretty much sums up process hollowing. It will basically inject an executable into another process's memory and remove the original process, so wipe svchost.exe from the process memory, and change the thread context so it points to its own process. So yeah, that sums up the process hollowing. And compared to DLL injection, it's actually quite common nowadays to see process hollowing, although most of the time it's paired up with another injection method like process doppelganging, which we'll see when we come to actually cover process doppelganging. So as I said, that wraps up the process hollowing stuff. Let's go ahead and move on to the next injection technique.